Right, okay. Developer's Guide to Containers and the Google Cloud Platform. How many of you know what the Google Cloud Platform is? Okay, good. That's getting better. We keep coming to Paris, so we have a big impact. If we went to Marseille, we probably wouldn't get so many people with their hands up. So we need to go to Marseille more, probably. Well, we went to Nantes, and we've been lots of other DevFests as well. So this is my talk on containers. How many of you are familiar with containers? And how many of you went to David's talk earlier? Okay, a bit of a cross-section, okay. So this isn't going to be a kind of basics on containers talk. I've left that for David, but it looks like there's some of you may not be that familiar with containers, so I should probably just cover some of that to begin with. Position things, and we're going to talk about containers everywhere. And we don't use the word Docker very much. Docker's great, but ultimately we need containers. And there may be one day lots of different competing container formats. So we talk generally about containers, but we're generally also talking about Docker. Oh, more agenda. Containers in the Google Cloud Platform. So we want to be able to have these containers running somewhere. You can run them on your laptop today using Docker. You can run them on PCs. You can run them on various different places, but you want to run them at scale. So we're going to talk about running containers on virtual machines. Then we're going to talk about Kubernetes, and we can talk about scheduling, taking containers and saying, I want to run containers. I don't care where you run them, just schedule them for me. And then we're going to look at a production version of Kubernetes called Google Container Engine, which was announced back in November, and which is not production ready yet. It's still in alpha, but it will be a production version of Kubernetes. How many of you have heard of Kubernetes? Who knows what Kubernetes means? Somebody? Pilot or helmsman, or yeah. So like helmsman of a ship, steersman or pilot or something like that. It's a Greek word. I should have a prize to give away for that. I really should. I apologise for not. I'm going to bring books, computing engine books with me next time. So what is a container? A container is a jar of M&Ms, apparently. But it's also a very lightweight and portable, I added portable last night, environment for running applications. So the ability to actually have your applications encapsulated in some kind of thing that you can move around between different runtimes. The ability to run applications on a single host, but which are isolated from each other. They're isolated from each other so they can't interfere with each other, and so they can't hog resources and effectively bring one down. So like if we have one container on the machine, using up all of the CPU on the machine, any other containers on that machine would go down because of it. So we have this kind of idea of isolating containers from each other. And then we move ultimately from the idea of having idealized hardware, which is what we have with the hypervisor, virtual machines, etc., to moving a layer above and having the idea of an idealized operating system. And containers, of course, have been recently popularized by Docker. So the last question is, how many of you have heard of Docker? Yeah. How many of you have actually spun up a Docker container? Right. So I want to see the people who didn't put their hands up for both of them. But yeah, so a lot of people have heard of Docker, but not everybody's spun up a Docker container. So why do developers care? Because of dogs, of course, but mainly because it provides reliable deployments. So we want to be able to run the same code in the same way, regardless of the product lifecycle. So if it's in test, if it's in development, if it's in prod, we want it to run in the same environment. We don't want these issues where it ran fine in test. You've probably seen that slide with a girl with the house burned down, saying, well, it ran fine in test or in QA. You want to be able to run equally well in production as you do in test. And so this gives you reliable deployments. It's a completely static application environment that doesn't change from one place to another. You're effectively carrying your environment, your runtime environment around with you in the container. There's also then the repeatability aspect of that and the portability. Because it's in a container, because it's self-contained, it can run anywhere where that container runtime, in this case Docker, can be run. And Docker can run on any Linux machine. It can actually run on Windows and Mac OS through some trickery. But effectively, Docker containers will run anywhere where you can run Docker. So you can run them on your laptop in development, then you can move them to production on a cloud, Amazon cloud, onto Mesosphere, something like that, or to Google Cloud Platform, and it will run exactly the same. And then finally, we're moving away from the concept of service-oriented architectures towards this idea of microservices, slightly lower down, smaller components than service-oriented architecture offered. But again, we can mix and match these containers to compose larger applications. And this is the marketing slide, and I hate this slide. Didn't put it in there for any reason other than just to upset the marketing people. So this is the real slide with dogs and Lego bricks and suitcases, and this is the marketing slide. Which do you prefer? The important thing is that everything at Google runs in a container. So we came up with this idea a long time ago that we couldn't just spend time building stuff on a machine somewhere. We wanted the notion of being able to configure something, provide a configuration file, provide the application runtime, and say to some kind of scheduler, hey, run this for me. Give me complete resource isolation, and give me priorities. Priorities are extremely important at Google. We have the idea of these jobs running everywhere across our clusters, huge clusters. And sometimes we have a really high priority job running on the same machine as a low priority job. One thing we cannot risk is that low priority job bringing down a high priority job. So we have to kind of balance everything out, and we have to kind of work out where these things should go. And we leave that up to an intelligent scheduler. And that used to be called Borg, and we couldn't use that term because of Star Trek, because of Paramount Pictures. That's the only reason we couldn't talk about it. And now we have Omega, which is the next generation of our scheduler. And we're going to talk about scheduling soon as well. It gives us more predictability. So again, those priorities, we understand better exactly how these things are going to run. The quality of service aspects as well come out of that. Being able to prioritize, being able to say, I want this service to have more priority than these other services. The ability to overcommit on demand. And overcommit effectively means saying, I want more CPU at this stage. I'm capped, I can't go above this, but for this particular moment in time, I need more CPU, or I need more memory, or I need more network bandwidth. For a small period of time, I want to overcommit. Then we have things like resource accounting as well, because containers are much easier to manage when it comes to accounting, because they're all the same thing. We're running a container somewhere. We don't really care about what it does underneath the hood, but we do care about how many resources it consumes while it's running. And this is what we had to begin with. Well, originally we had machines with no hypervisor, but now we have virtual machines, and virtual machines look something like this. We have this layer of idealized hardware presented to us by the hypervisor. And that will allow us effectively to run multiple versions of the operating system on top of the hardware. And that's what virtual machines are effectively. So if you buy a VMware cluster or something like that, you can have multiple machines all run on the same piece of hardware. And that's great. That's the original idealized hardware virtualization model. But we have some problems. These kind of problems are a little bit exaggerated. We've all ran multiple applications on the same machine before. Everybody has. It can be a problem, and it can be a new problem when you're bringing in new stuff you're not familiar with. But the fact is that applications running on a virtual machine will share stuff. They'll share libraries. They'll share things that could actually change underneath them. So one application running along happily, some dependency gets updated, which is fine for the other application, but not fine for it. It has no control over its dependencies. So we have a bit of a problem, no isolation. And also reuse-wise, we get this situation. We have this idealized hardware, we have the hypervisor, we have 3 virtual machines running on top of that hypervisor. And again, you can see the reuse here is not great. We have 3 different versions, or 3 versions could be absolutely identical of the same operating system running on top of that hypervisor. We have achieved isolation for our application code, but by having these kind of heavyweight virtual machines to run the application. So we've achieved isolation at the cost of reuse and the cost of having heavyweight virtual machines. We know how long they take to spin up as well. Containers effectively create a better, or at least a different abstraction layer. And they move us up the stack. So we have an idealized operating system, the guest kernel in this case, instead of an idealized piece of hardware. And on top of that, we can run our libraries as before and our application code within a container. And that would look something like this. So we have the hypervisor as before. We have what we now call our node kernel. Now we're starting to talk about clusters and use cluster terminology. So we have a node, we have the node OS, its kernel running on top of the hypervisor, and that has all of the stuff we need to be able to run containers. So in this case, we have 3 containers, all probably running different applications, and all sitting on top of this virtualized, idealized operating system. And they're all completely isolated, but we only have one version of this. Okay, got that? Any questions? Okay.
Does Google actually run hypervisors and then containers on?
We use the KVM, so yeah, we use KVM extensively, but secret source as well, so it's not. Anything that comes into Google, the engineers kind of like jump on like vultures and say, oh, yes, this doesn't work very well, let's fix this. Often we put stuff back to the community as well, which is great. So sometimes these things aren't open source and we just have to kind of work with them as best we can. So we had this situation where we have a node running containers, but what we really want is this situation where we have lots of these nodes running lots of containers. But we don't really want to have to be the ones to go and say, I want to run this container on this node. We want to do things differently, so we want to use some kind of scheduler like we do at Google. This is what we do at Google effectively. So this blue bit down here, the managed base OS and the node container manager, that configuration will be found on every machine running at Google, every virtual machine running at Google, every physical machine running at Google. So you'll always find that, and we're going to be running our stuff on top of it. But instead of having our engineer who wants to run Gmail or search or a canary version of YouTube, a new non-production version of YouTube, to run some tests, to do anything, we don't want him to have to go to a data center, not physically, of course, but via an SSH prompt or something. We don't want to go to a data center, to a rack, to a machine and say, I want to run it on here. That's not going to work for us. We have a lot of machines at Google. And we had a lot of machines when I started, and we probably have even more now. We should count these things in cores, not in machines. And so what we want to be able to do is have the engineer effectively declare what he wants. I want 10 of these. I want X number of replicas. I want X amount of CPU. I want Y amount of memory. I want this amount of network bandwidth. I want it to be fully redundant. And run this for me. And he passes it on to the scheduler, which could be Omega, our latest scheduler. And the cluster scheduler will take care of running it for him. Again, it takes into consideration all of these things like prioritization. We also have these things like bin packing and starving, that kind of thing, where we have points where we want to get the utilization of the machine to be the maximum possible, as opposed to having lots of CPU, all of the CPU maxed out, but only half the memory. Those kind of things give us situations where we have lots of memory free, but no CPU. We can't run anything else in that machine, but we're not using all of its memory. So it does lots of balancing and things like that and jiggling things around to make sure that the job runs correctly. So it takes into think all of those instructions the engineers passed on to it, and it runs and schedules these containers, these workloads, wherever it can. And so we come to this notion of imperative versus declarative. And imperative is that thing where the engineer says explicitly, I want to run this thing in this data center, on this rack, on this machine. And we move to keep 100 copies of this container running at all times. And this is kind of resilient to failures. The scheduler can monitor to make sure that the desired state, what was originally in that configuration file, is maintained all of the time. It's also easy to update, and it supports the delegation of ultimately of responsibilities. So that's what we do at Google in simple terms. It's probably a lot more complicated than that. So the whole idea of Kubernetes and the whole idea of Container Engine, which is a production version of Kubernetes, is to allow people to do that outside of Google. So the first thing we're going to look at is the idea of a simple situation where we want to run containers on a virtual machine. And we're not going to look at the big picture yet. That comes when we look at Kubernetes. So the first thing we need to do is recreate this situation where we have what we had at Google. Node container manager, managed base OS. We have that running on a virtual machine in the cloud somewhere, in the public cloud, where you guys, everybody else can access it. So for this, it's described in the green box what we have. We have the notion of container optimized VMs and container optimized virtual machine images, which can be used to provision those VMs. And what that effectively does, it builds up Debian, installs Docker at the top, sticks a small scheduler on it, which is called a kubelet, and runs your containers for you. It will monitor the health of the containers and it will restart them as needed. And we get to the declarative part as well. We actually configure this via a manifest file, a YAML file, which we pass in when we provision the machine. And that will say what containers we want to run, how many of them we want to run. We will let this scheduler component handle it all for us. And that looks something like this. So we have one of these crazy commands, gcloud compute. Gcloud is our cloud SDK. And it's basically like one tool to rule them all. Yeah, so we have gcloud compute, gcloud app, gcloud this, that, and the other to do everything in Google Cloud Platform. This command is actually creating an instance called my nginx container. Now this is the way you create instances generally. So this is in Compute Engine, which is our infrastructure as a service offering, provides virtual machines in the cloud. You guys familiar with Compute Engine? Maybe some of you are. Okay. So but anyway, the idea is we will provision virtual machines on demand in the cloud. These virtual machines come and go on demand as we need them, and the idea of actually having to worry about them too much is no longer relevant. You just spin them up when you need them, you take them away when you don't. So in this case, we're creating a new virtual machine. We have some standard parameters here, like the zone. So we have the idea of zones where you can run your virtual machines. We have 3 regions, US, EMEA, and APAC. And within each zone, we have each region we have 3 zones, except in Europe, where we only have 2 for some reason. They don't like Europe in the US. But anyway, we had the capacity, but we had this idea of zones where you're going to run your virtual machines. Also the machine type, in this case F1 micro, this is a very small instance. It's a shared core instance. It shares cores with other virtual machines of the same type. We can go bigger. We can have 16 core virtual machines if we wanted to. But you know, these things are going to be fairly lightweight probably, so having smaller versions of these virtual machines to run the jobs is probably better, but it depends on what your workload is. Now we get into the more specifics. Here we're going to provide an image, and this is effectively the image we're going to use to revision the virtual machine with. This is an OS image, and I think by default we have Debian with Docker installed on top. So this is what that image is, probably out of date by now. And also we have to specify the scope of where that container virtual machine image can be found, Google Containers. And then we have the ability to provide or pass in metadata to a virtual machine or to a project when we create it. And in this case, we're saying the metadata, Google Container Manifest, will be this file containers.yaml. Now, our gcloud command is kind of smart. It can look in a local directory when you're deploying this to find your containers.yaml file. And this is what we go back to, what the engineer at Google provides in order to run his jobs. So we have this idea of declaring what you want to do in a file called containers.yaml locally, what containers you want, in this case www, using a top-level Docker image. And again, this is an image used to initialize and to create containers. Nginx is a top-level Docker image that effectively installs Nginx for you. And then we need to map ports as well. So for Nginx, we're going to need to map a port. In this case, we map port 8080 on the host to port 80 on the container. So this is the container here. This is the virtual machine. We're mapping port 80 on the container to 8080 on the host. So now anybody can connect, well, providing you've got firewall rules set up appropriately, anyone can connect to this container via port 8080 on this virtual machine. Again, you need to know where the virtual machine is, right? You need to know its IP address or its DNS address or something like that. So that's kind of limited already. Another example, just to bring in this notion that sometimes containers have this kind of synergy where they live and die together. They like each other so much that you only had them together. You never have one alone. In this case, we have a, say, Nginx server with a CMS such as Sinatra or Jekyll, which is feeding effectively data into the web server. And the web server is serving the generated HTML content from the CMS. And they share data via a disk volume. And basically here we can configure containers, WW and CMS. We have a data volume. I think there's more to it than that. And we're mapping that here as read-only on /mnt data vol, and down here as read-write as data volume /mnt/output. So the CMS can now write to this volume, and the web server can now read from it. So effectively they're working together. When we don't want the web server anymore, we also don't want the CMS, so we're taking them both away together. And that's important, because we're going to come back to that in a second. So the next part of it is scheduling. So we have this very basic scheduler currently on this virtual machine which we provisioned. We only have one virtual machine, but we can schedule containers on it. But we want to go back to this situation where we have lots of these. We have a fabric, effectively, of virtual machines, or virtual resources on which we can deploy containers. So we want to be able to schedule across machines, we want to be able to do replication, we want to be able to do resizing, and we want to create services, because we don't want to have this situation where we have to find what the IP address is of the virtual machine, what port the application is running on, etc. So Kubernetes. So I'm going to quickly see if the Wi-Fi is working. Yay! Hello. So I'm going to create a cluster. Everybody see that, or is it too low down? I'll move it up. Anybody not be able to see it at the bottom? I want to do a visualization in a minute, and I want to have the command line at the bottom. I can move it to the top if need be. Now you can see it? Yeah? Okay, so gcloud command, which is the SDK we talked about earlier. Preview, container. I should have command line completion, but it seems to have broken on me. So I have to actually type it. And I'm going to create a cluster called guestbook. So I'll run that now. And that's going to go off and create a cluster, a Kubernetes cluster for us. And we're going to circle back on this in a second because it's going to take a few minutes to do. Okay, so this is why I'm starting it now, because I don't want you sitting there watching it, counting the time. So, back to these slides. Right, so we're creating a Kubernetes cluster using Google Container Engine, and we're going to clarify those points now. So Kubernetes, some of you have heard of it, some of you know what it means. I don't think what it means is particularly relevant. It's helmsman of a ship, that kind of thing. But effectively, what Kubernetes is a container cluster scheduler. And we can use it to build clusters of machines and then effectively manage container deployments on those machines. The project itself is completely open source, Apache 2 license, 0.9 version release so far, and so we're heading very quickly towards 1.0. I think we might slow down a little bit before we get there, but 1.0 is going to be around soon. 197 contributors on GitHub. We have 5,900 GitHub stars, which is good if you know GitHub. We have lots of different partners all working on it. We introduced Kubernetes, but everybody else has picked up on it. I actually looking on DigitalOcean's website today, and they have a great explanation of what Kubernetes is. Everybody is into Kubernetes. So it's not just Google. You can run this anywhere. It's a multi-cloud solution. And the idea is that it should be lean, extensible, and portable. It is written in Go, which is a good thing. Anything written in Go is a good thing. And I'm learning that myself. So everybody should write things in Go. Just forget the other language. No, sorry, I didn't say that. And we go to this idea of managing applications, not machines. We don't care about machines. We just want this fabric of machines, this big pool of compute resources on which we can run stuff. We don't want to care about that machine there called Gron, that machine called Tech Girl, this, that, and the other. And it's my Twitter handle, by the way. We don't want to have to worry about that. We just want to worry about deploying applications across all of our infrastructure. So the idea of a pod, and this comes back to what we looked at earlier with two containers sharing stuff. Looking at the time, sorry. Two containers sharing stuff. So the scheduling resource we're going to be talking about in Kubernetes is called a pod. And a pod is effectively a collection of containers. And they're collected in such a way that they have that kind of synergy. They have a synergy. I can't say that word. I think my mouth's dry. Synergistic relationship. So in this case, we have our World Wide Web server, Nginx or whatever, and a CMS, Jekyll and Sinatra, running together. Containers are paired together effectively, and live and die together within a pod. And this pod can contain much other things. We have some examples as well. But effectively, this is what we're going to be scheduling. not containers specifically, but pods, which is groups of containers. These are defined declaratively in a template. Again, we've ticked off another checkbox. We want to be able to declare these things after we build them. We have to create images, but we declare how we're going to deploy those containers, the actual things that the images build. We have lots of reuse across the environments that we deploy to, so we could deploy this pod to different Kubernetes clusters if we wanted to. But the idea of a pod is that it has no identity. People use this horrible analogy of things like cattle versus pets. And these containers, I'm not going to use that. I don't like that analogy because it suggests we treat cattle really badly, but we don't care about this thing. We're not going to give it a name. We want one of them, but we don't care what it is, where it's running, or anything like that. All we care is that it is running. So we can run this across different environments, and it's completely repeatable. We can have multiple different copies of it, and it can be managed. And pods effectively look like this. This is kind of a higher level of abstraction. We have a pod, we have the Kubernetes master scheduler, and we have a fabric of machines. 4 different virtual machines in this case. This could be tens of thousands of virtual machines. Many, many more if it's Google. So we're effectively saying, I want to run this pod, run it somewhere for me. Some more examples of this synergistic relationship, I can say it now. We looked at CMS systems which have file and data loaders, local caches and managers, etc. Those containers would be shared within a pod. Login and checkpointing backups, compression, rotation, snapshotting, all things that run as individual tasks as different containers, but would run together. Data change watchers, log tailors, logging and monitoring, all of these things together as individual containers within a pod. Things like proxies, bridges and adapters, controllers, managers, configurators, updaters. Anything that has that kind of relationship. You'll know when you need this kind of thing, when you have to run multiple processes to get your application up and running. So if you're running Redis or something like that, or Redis and a web server, that kind of thing, they have this kind of relationship. So also going back to how we share data across these containers, that's really important. And again, this question came up a few times when I've given this talk in the past. So we have the idea of volumes, going back to that slide from earlier, where we have 2 containers with a shared volume. At the moment, the different types of volumes we can have with Kubernetes are one that's called an empty dir, which effectively lives and dies with the pod. So it's created when the pod's created. The containers can share data via this empty dir volume. But once the containers in the pod go away, it goes away as well. So it's not persisted in any way. Then there's the hoster, which effectively allows you to access the files on the virtual machine. We don't really encourage this because the virtual machine isn't the container, and the state on the virtual machine may be different from what you expect from one machine to another. Remember, this pod has no idea where it's running, but its view of the file system, or the file system on which it's running, may be different depending on where it's running on. So the container may actually be seeing side effects by changes to the file system. So we don't recommend actually mapping the host directory, the file system, into the container. But it is possible to do that. And the other way as well is with Google Cloud Platform, we have this thing called a GCU persistent disk, and we can effectively map the volume to a location on a virtual persistent disk that we provide in the cloud. So that's specific to Google Cloud Platform. The next thing is labels. And labels are used everywhere within Kubernetes. Everything can have a label. The use of labels can be completely down to you. You can look at the labels of these artifacts that are running, but we also have services and replication controllers within Kubernetes that already make use of labels. So you can create these labels yourself, use them for your own dashboards, those kind of things. You can be looking at your pods with certain labels and maybe graphing them and that kind of thing, or monitoring them. But also Kubernetes is monitoring these labels as well with some of its other artifacts, and we'll look at those shortly. So in this case, we have a dashboard application, maybe one you've written, 2 of them, that one there, this one here. We have 3 pods, 2 of them labeled with FE, that's a label. These are key value pairs, these labels. They're not just labels, not just strings, they are key value pairs. So you can say like name equals FE, or name equals V2, or role. Role is also important as well. So they are more complicated than just strings that we attach to the pod. So in this case, we're saying name equals FE, name equals FE, name equals V2. This dashboard is using some kind of selector to say, I'm interested in pods that are labeled FE. I'm interested in pods that are labeled V2. So we have different dashboards looking at different aspects of our runtime. And again, these pods can be run anywhere. So all I'm saying is that I'm interested in any pods run anywhere with the label FE. Replication controllers. So this is a slide I wrote a long time ago before this one came out. And a replication controller is effectively a pod factory. I like that. It creates and manages a set of pods based on a template that you provide. And we'll look at this shortly. It effectively ensures that the required number of pods of a particular type, or lots of different pods of particular types, are running. And it creates and kills pods as required. So if we say we want 4 of these pods running in our cluster, it will make sure there's 4. If we have 5, it will kill one off. Maybe somebody spawned another one, or maybe there was some kind of race condition where one was going down and one was coming up, and we end up with 5 rather than the 4 that we needed. It would kill one off. If there were 3, it would bring another one up. Again, cattle versus pets. I really don't want to use that analogy. So the replication controller is effectively looking at pods with labels. So we can have pods independently of replication controllers. We don't need to have a replication controller. But we can say, when we create a replication controller, I want 6 pods labeled V1. And it will create them for you, and it will monitor them for you and manage their state. We have this notion of desired state. We want 10 of these things running. We want their ports mapped in a certain way. It will make sure that that's happening. The desired state is all important here. It will maintain the desired state for us. So in this case, this replication controller has 2 pods it cares about. It has a selector on labels for V1. So these are V1 pods. This is a V2 pod, and this has a selector for V2. So this replication controller is managing all pods with label V2. Yeah, makes sense? Okay. The last thing is services, because we want to pull all of these things together into something that we can actually expose to the outside world. So we have lots of different containers running, which may all be part of one single application, which is exposed as a service. And the service is effectively a front end that can expose a port to the outside world. Uses things like IP tables for mapping and such like, but effectively we have one IP address across a whole fleet of machines exposing our service. And services, again, use selectors. So we have the selector FE. This service only cares about pods with the label FE, and it will hook all of those up together and effectively load balance work across those machines. Containers. Machines, what a terrible word. So it will load balance the work across these pods labeled FE. Yeah? I'll show you this working. As an example, I'm going to skip over that because I want to show you my demo. First, talk about Google Container Engine. I mentioned this before. This is currently in alpha. This is a production version of Kubernetes, or it will be once it reaches general availability. It's available to use by anybody. Usually our alphas are closed. You have to sign up for a whitelist. But this is available. You go to cloud.google.com/console and you will have access to Container Engine. Yes?
Can you give an example of when the replication, how you use the replication? What's the typical use case?
Yeah, so I think I'll go through my demo and show you, and see if it comes clearer when I show you that. It's basically about scale, right? So it's basically if you need more or you need less. And you can dynamically configure these things so that they can grow and shrink on demand. So, designed for a multi-cloud world. Container Engine obviously works in Google Cloud Platform. One day I imagine that these things will all be linked together. Public clouds, it won't matter what cloud you're using, you'll have one fabric. You may have some machines on Amazon, you may have some machines on Google Cloud Platform. You may be able to pull everything in across multiple different providers. At the moment, this is limited to Google Cloud Platform. Container Engine is effectively, as I said, Kubernetes, but made available to people as a supportable service with SLAs, guarantees, and that kind of thing, but not available yet because it's still in alpha. These things, have we covered them all? So desired state, Kubernetes, alpha, SLA and pricing will come when it becomes GA. But anyway, we've seen what container engine is by looking at Kubernetes. And there's an architectural diagram of it, which isn't a particularly great representation of it. We're talking about Kubernetes again. I'm going to go into the demo. So I'm excited for my demo. See how much time I've got. Right, I've got 9 minutes. Okay. So this is the Cloud Console. We have a project called Kubernetes. And Google Cloud, or Developers Console, sorry. I called it the Cloud Console. I do apologize. It's the Developers Console because it gives you access to other APIs as well, such as maps, those kind of things. But it also gives you access to everything in cloud. And the thing we care about here, if I can scroll properly, virtual machine instances, we should have some now because our cluster has been built, as we can see down here. Again, if you can't see it, tell me and I'll move it up. But now we have a cluster of machines. We have 3 nodes, not called minions, they're called nodes. And we have a master, a Kubernetes master. And we care about the Kubernetes master because we're going to talk to it using a proxy. So we can see what's going on. I need its IP address. So that's our master. I'm going to quickly spin over to a different window. And I'm going to run this really horrible command, which I can make simpler, but I'm not going to. And this is just a proxy command that allows me to see things that are going on within the master. And this is our visualization. This is going to visualize what a Kubernetes cluster looks like once it's been deployed. Okay, so empty, there's nothing there. So we have a cluster, we have these machines, this fabric of machines that we can use to run stuff, but we're not running anything currently. So the first thing to do, and I'm going to cut and paste here, I do apologize for that, but it's kind of tough to remember all of these commands. Actually, I've remembered them. I can type them with my eyes closed, because I've done them so many times. Move that up a bit. So here we're going to create a Redis master pod. We're just going to create a pod. Yeah? This is a Redis master. We only want one of them. Okay, so we're going to create a pod that is effectively a Redis master. And I'm going to run this command now.
What's inside the JSON?
Sorry?
What is inside the JSON?
I'll show you now. I don't have all of them because looking at JSON files is quite boring, generally, like XML. But I do have some of them. So go back to present. I don't want to spend too much time on the JSON. Come on, connect, connect, connect. So this is the Redis master pod JSON. It's a pod. And again, we can have services, replication controllers and such like specified within a config file. In this case, we're saying a pod. Our desired state is we want this container. This is a pod. We have one container in this currently. We could have multiple containers. Again, going back to pods having multiple containers. In this case, we only have one, which is a Redis master. And going back to the demo, we'll find it.
So what is the advantage of having that one container in that one pod?
Because this is a Redis master. There's no synergistic relationship with anything else. We just want to run the Redis master somewhere. You're only ever going to have one of them. The system can make sure there's always one of them running. Obviously, with Redis, that may be a bit more complicated because you have workers and such like talking to that master. The master goes away, you need to make sure it comes back in a certain way with the right environment variable set. But in this case, we need one Redis master. Okay, so the next thing we need to do is create a service. And that's going to be and that will create a service for us. And now this effectively is exposing the pod, the Redis master pod, internally to the rest of the cluster. We've not exposed this externally. We don't want to talk to Redis. We want our application to talk to Redis. So I'm going to quickly spin through these because I know we're short on time. The next thing we want to do is create a replication controller. And here we have the same command again, gcloud preview container, replication controllers create, and a config file. In this case, a controller specific config file. And this will create our Redis workers for us. And there's our Redis workers talking to the Redis master. So we have the replication controller managing the pods, and we have the pods themselves are talking to the Redis master service. So they need to talk to the service, right? Because it's a master. And that's the master service, and that's what the controller looks like. I've taken out the pod stuff in the middle, but that's what the actual replication controller configuration looks like. Replication controller, I want 2 of these, and I want to select based on these labels: name, Redis, role, worker, and my pod definition is below. Whoops. And that's the next one, which is specified there. And again, it's a container specification. We have a specific image used and a set of labels which kind of tie into what we used before for the selector. Keep going the wrong way. So the next thing to do is just run through these ones fairly quickly. We've seen examples of them already. And clear on there. Go back to the visualization. In this case, we're going to create the worker service, and we need our application to talk to the worker. This is how it will access Redis. So now we have a service up here, Redis worker, and the next thing we're going to do is create the actual application itself. And for that, I'm going to take these 2 commands and I'm going to cut and paste them together to save time. So we're going to create a guestbook controller, replication controllers create, and a service, services create. This service is a little bit different though, because it's going to be exposed to the outside world. So let's quickly run this one. And that takes a little bit longer. So now we have our guestbook controller here managing 3 pods, which are running PHP effectively, our PHP application. And they are talking to the Redis workers via the Redis worker service. And the final thing we have is the guestbook service up here. And that is exposing an IP address to the outside world, which we can access. And in this case, I'm going to clear. And this has effectively created a load balancer within Google Cloud Platform. So I'm just going to quickly list what the IP address is. So I have this idea of a forwarding rule for a load balancer. This is the entry point to the load balancer. I'm going to take that IP address, and I'm going to go up here and connect to port 3000, which is what we expose in the service, which I've not shown you yet. I'll show you shortly. And for some reason my application is not working. Oh no, please work. Okay, interesting. The demo gods have got me again. It's worked fine earlier. There's no reason for you not to work. Work. No.
Maybe Wi-Fi filter.
Sorry?
Wi-Fi may filter the port 3000.
Maybe. Maybe blocking the port.
Yeah.
May not like so because it's a university campus type Wi-Fi. Can I tether to the phone and try it on there?
Can you try again? It's on. Can you use it?
See if it can make it work. Connect. It's still trying to connect.
It's working for me.
Yeah,
It's working for me.
Yeah. Is the phone on properly? Have you got signal?
oh yeah.
Well, anyway, you guys can connect to that IP address on port 3000. I can't. And, oh, what a shame. I'm tempted to turn Wi-Fi off here. And try again. Aha, better. So now we try again. And it still doesn't work. Who said they got it working? So you got the guestbook app?
Yes.
Okay. Okay, so
If you want.
brilliant. Okay, so
You could
anyway,
plug
so
it in if you want.
So well, you got H.
Plug it in?
No, that's all right. Don't
You
worry.
can.
Why is it? That's really weird. Oh, it's still connected back to Laureate Guest. Of course it did. But anyway, you guys can connect to it and you can send messages. Nice, clean messages. Not. Now it's worked. Right, so we have a very simple guestbook. So we went through that. We have a Redis master, we have Redis slaves, we have an application with 3 pods, talking to the Redis workers, talking to the Redis master, and it's I can't type now, I'm flustered. Hey, I can't zoom. Might zoom, all right. Anyway, so I can click submit on that and it will say, hello DevFest Paris. So basically we have that architecture. So that's done. And again, so the PHP Redis, in answer to your question from earlier, the PHP Redis application that's talking to Redis has 3 pods. Obviously, if we wanted to scale that, and we don't have any kind of automatic scalability at the moment, but if we wanted to scale it to handle thousands, hundreds of thousands of users, we would have more pods. We could wire that up at the moment using some manual method to automatically scale on demand. So we could monitor the utilization and such like and add more pods as needed, take pods away when they're not needed. Yeah. And thank you for your patience. Sorry that didn't work out so well. That's what the visualization looks like. So we effectively have a forwarding rule at the top there, incoming requests go to the guestbook, and everything is wired up together via labels and selectors, that kind of thing. And finally, if you want to try Google Cloud Platform Container Engine, we have a free trial. And I really recommend you try this out. It's just like, there's no commitment. Once you've spent the money, it will say, hey, you spent the money, or you've run out of time. Do you want to upgrade your account to a real paying account? And you can click a button and say yes. If you run over $300, it will stop. It won't start charging your credit card or anything like that. So it's completely safe. Go ahead and try it. Spin up a cluster of your own. You only have a limited amount of quota. So we can probably help with that if you need to. But $300 in Cloud Platform credits, go out and try it. And basically, thank you. And we've kind of almost run out of time for questions, but we've got time for a couple of questions.
Yeah, well, it's your time.
A couple of quick questions, thank you.
How would you compare Kubernetes to Helios and Docker Swarm?
No idea. Not used Helios or Docker Swarm. Well, how would you compare them?
Well, no, I was just
Have
wondering,
you-
like, what's like the selling point of Kubernetes? Because Helios is by Spotify, their orchestration platform across the fleet.
Mm-hmm.
It's kind of badass. But I mean,
I shall check them out.
Docker Swarm is like the native,
Yeah.
supported by Docker.
Yeah.
Right out of the box.
Yeah, I focus specifically on Kubernetes. I've not actually looked at anything else. So I do apologise for that, but yeah.
How did you manage to have the dashboard, Cube CFG? It is
Right, okay, so that's a proxy, yeah. So we have, we're using JS Plum for the, JS Plum does all of the wiring for us. So this is just basic JavaScript. And we have a proxy. So effectively what we're running locally, kubecfg or now kubectl, CTL, you use to effectively connect to the proxy server on the master, which has an API server as well. And you can then make API requests to the API server, get the information about the pods, replication controllers, services, etc. back, and build the model from that.
Okay. I use the Google Container Engine.
Yeah.
I didn't see this.
No, this was written for a demo specifically, so
Okay.
I can point you to the code. It's on GitHub.
Okay.
In fact, I can probably just do that now. I hope I can find it quickly. If not, I'll drop me an email. Oh, there it is. I can't make the. So it's Brendan Burns /GCP-live-K8-visualizer. But again, you have to work the labels a little bit to make it work. And my version's a little bit cleaner.
Okay.
I can share the code with you if you want to.
Okay.
Yeah. Right. So yeah. Any other questions? Thank you. I appreciate it. Oh, sorry.